Section 3, design criteria. Now this is one of the most important part of the design process is, or design activity is developing the design criteria. What does it mean, design criteria? Now, if you are all designing one building, every one of you will come up with different design, different answers, right? No two engineers can design the building exactly in the same way. So if somebody has to come and check your work, then obviously they will debate with you on everything. So for that purpose and for everybody's clarity, we need to clearly write what is the basis of your design. So this is typically the content of a typical design criteria document. So you must make this document first, which will be the basis for your design, and you try to write down everything in this document. So anybody, the client or anybody who's going to check your design, they will first read your design criteria and say whether your criteria is correct or not. If the criteria is not good, no point to check calculations. And if the criteria is good, they agree with the criteria, then next steps are possible. But if they disagree something that you use, assumptions that you use, the process you use, then you cannot go along. So the first step is to write a good design criteria document. And again, many engineers do not know how to write a good design criteria document. So that is something that you would be required to do when you do your project. First will be to write the design criteria, which you will submit as an assignment separately, which then will go to assist in your project. So design criteria looks something like this. First of all, introduction to the building, where you have to describe, so I will go into the details of each one of them. So this is the overall content of a design criteria. Let's see the details now. So building description and location. So this is important because this will determine the wind loading, earthquake forces, and other location-based information like geotechnical and other things, right? So that's why it is important to describe the building, where it is located, and what are these seismic and wind forces resisting systems that you will use, and then you will write the codes and the drawings to be made. So basically, building description will come what you plan to do overall for this building, and codes and references will go there. Loading criteria, most important part of the design document will be, okay, let me just go back again and go through this a little bit more. So building information like this one, and then load criteria, second part, which will describe all of the loads that you are going to use, and then materials that you are going to use in your project, and then strengths and so on, and then modeling analysis procedure that you are going to use. Because these are the areas where people will argue with you. Loading, they will argue with you systems, they will argue with you on analysis procedures. So normally the arguments must be settled at this level, and once everybody agree, then the calculation is just a follow-up from that, right? So let's go to these loading criteria. Now, this one is something that is very important in this process to understand that we never design anything for loads. I mentioned that before also maybe. We design things for the possible combination of effects of loads, right? So the design is very far from the load. That load, but the design has nothing to do directly with that load. You say the dead load here, or the live load, let's say live load. You say the live load here is 40 pounds per square foot or 2 kilonewton per square meter, right? But the reinforcement is not calculated based on this load number. This load number must first be applied on the members, transferred to various members, calculate bending moment, shear forces and all those actions. then combined, then multiplied by some factors, then combined with some other loading, possible loading, then come up with a number for which the reinforcement will be designed. So that process is shown here. Loads, load cases. Load cases mean the application of the loads in different forms. Load combinations, that means combining different load cases together, possibility of different load cases coming at the same time with the probability of combination. And then from there, design envelope and then design actions. Now, typically, design envelopes, we do not use. What is a design envelope? Last time I think I mentioned. What is an envelope? Something we put in, right? It's a bound, it's a boundary. So, envelope means maximum and minimum numbers, but they are not useful to us. You cannot design for maximum moment, maximum, we talked about that, right? So, we need action sets. So, design actions, we come from load combinations and directly we can go to design action, and we skip the envelope part, which may be relevant for steel, which may be relevant for pre-stressed concrete. Last time we talked about that. The pre-stressed concrete is just like elastic material. Interaction is not really considered, so elastic envelope can be used there. So sometimes we go through this one, sometimes we jump like this one. But the whole process, what loads you will use, what cases you will use, what combinations you will use, and what design actions you will use should be described clearly in your design criteria. Load cases. Load cases are defined by the user and are used for analysis purposes only. They are not used for design, only used for analysis. That means to find out the response for a particular load. Why do we call it load case? That means a particular loading location. For example, if I'm standing here, then I can calculate the bending moment for this slab with 1 point load, which is me, one load case. If I move here, another load case. If I move here, another load case. So we keep on moving the loads or applying the loads on for every possible application of load, there will be one load case. So if there is a bridge, moving load, how many load cases will there be for live load? Infinite. Because the load is moving all the time, little bit, 1 millimeter, 2 millimeter. So for every 1 millimeter move, there is another load case theoretically. And there is not one truck. There are hundreds of trucks and buses and cars and things moving all at the same time. So just try to imagine how many load cases you may want to create. Impossible, right? But in reality, that is how many load cases are there in a typical bridge system. Same is the case for live load. All the people sitting on this side, one live load. All the people sitting on this side, another live load case. That room has no students. This room has students, another live load case. So these are called load patterns. So every possible placement of load makes it one load case. So static load case is dead load, live load, wind load. Wind load, for example, coming from this direction, coming from that direction, this direction. How many wind directions are there? Infinity. Everywhere. Wind can come from any direction. So of course we don't consider infinity, we divide them into some directions and then do some logic. But in reality, we will never ever be able to cover all load cases that occur. So we try to find the one which will be important and critical. Right? So no matter what we do, we cannot consider all the possible load cases in a structure. This is just the problem of load cases. Earthquake, response spectrum cases, time history cases. We will touch upon this quite in detail later. Nonlinear, static nonlinear load cases. Then will come dynamic nonlinear load cases. So there will be many types of load cases. Now, this is one thing, not time changing. Time history analysis load case means just like vehicles moving with time. Earthquake, same thing. Earthquake is started, 0 time, every ground movement after every 0.001 or 0.01 second interval is a different load case. So for a typical earthquake which lasts 30 seconds, we will get around 4,000 load cases to be analyzed for one earthquake direction. Then earthquake can come from any directions, right? So you can imagine thousands upon thousands of load cases can generate, and their time bound also depend on the previous condition. So it is, and then during that time there will be non-linearity, cracking, so the structure will change. So not only the loads will change, but the structure that you modeled will also change. In the beginning there was no cracking. Now some columns start to crack, properties have changed, moment of inertia have changed. So we have to update the properties, we have also to update the cases, then continue, and if we find that this is too far, go back, try again, and so on and so forth. So these cases and application gradually runs into hundreds of thousands in the end, right? And this is just each load case. Then we are going to combine dead load and live load and wind load. We are going to combine dead load and live load and earthquake load, which earthquake, and so on. So combinations will become even much more, far more than quake cases. Because dead load must be combined with, let's say, 30 load wind direction, 36 wind direction, right, every 10-degree angle. And positive and negative, so, and if you have live load also, you also want to combine that. So it's really, if you really want to do in detail, it cannot be done. So we have to then say, okay, that's why design criteria is very important. You will define what load cases you will consider. How many wind directions are you going to consider? 1, 2, or 3? So it's important to specify load cases of all of these things, how many you will consider, how you will create them, and so on. Dead load alone, then you need to know the weight of all the materials that are involved, and you need to list them down, because these densities are not constant. Concrete, for example, may have different weight depending upon the aggregate that you are getting from. So you need to specify that concrete and cement, this one I'm going to use this, and then it has to be agreed. Some people may use 20 to 24, some people may use something else. So there is always a disagreement whether we use concrete without reinforcement or with reinforcement, because the weight will be different. But we don't know the reinforcement at the beginning, so how can we add the weight? So we estimate. So things like that. And then different stones that you use weigh differently. So if you make it from limestone, different weight, and other stones different weight. So that has to be all clearly mentioned in a table like this. Like what are your bases for calculating the loads, and where did you get from? Live load. This is quite complicated. Why? Because of the usage. Classroom, sleeping quarters, dancing floors, gymnasiums, library, depends on the use. That's why in advanced countries, in USA and other places, every room has a plate indicating this room is designed for this much live load, right? This building is designed for that many persons. Some hotels, they write this building is designed for 489 persons, not even 490 or 500, 489, because that's what they calculate. So if it is more than that, then responsibility shifts to the different people and so on and so forth. But we don't have that practice here. But many buildings, many rooms, they have a plate indicating what are these floors designed for, so that we don't exceed those usages. But there are so many tables. In fact, if you look at the design code, you will find about 10 pages full of live load criteria. So many possible usage, right? But again, the problem is that we cannot be sure the use will continue. So that's why there is a safety margin on that and load combination, which we will see later. But at least basic loads you must list based on the use that you know of that building. So which means different rooms will have to apply different live loads. Corridor different, room different. Now it's very interesting because it could be just one slab and part of that is a corridor, part of that is a room. So that means you need to apply a different live load for part of the slab and different live load on the rest of the slab. Things can easily happen. You divide this room, one room is another use, one room is another use, but the slab is one, right? So that means the same slab has to be designed partially for different live load, partially for different live load. So those situations arise and they have to be managed in the analysis. And that must be specified clearly. Now comes the seismic load. Seismic load is something that we will spend a lot of time. It is quite complex, quite complicated, depending upon the method that you will use. So things that you need to specify: seismic zone, seismic source type, importance factor, distance from the near source, soil profile type, dead load system. These are critical information that must be said that, okay, my building will be designed for this criteria, right? And it depends on location, seismic zone 4, highest, 3, medium, and so on. So you must have a seismic map where the zoning is marked, and from that you pick up. But now, these days, we specify that in the new code, we specify it in a different way. Wind, you specify basic wind speed, exposure, occupancy category, importance factor, and so on. All these again based in code. You should have wind maps to know where the wind velocity will be, right? Whether it's open, whether it's a city, in the open. Now, this is also very interesting. Today you build the building in an open space, tomorrow you build buildings all around that, your exposure condition has changed. Or you build the building somewhere and the people demolish the building around you, the exposure changes, right? Or you make a building and some people make the building in front of you or on the side on your side, completely changing the wind loading on your building. So these are all issues that you cannot control. That's why you need to write them in the design criteria. This is my basis. So if it changed, not my fault. Then comes the combinations. So cases, we have already talked about so many cases. Then the probability that they will work together or they will act together is what we need to think about. Again, these are based on old code, right? Do not believe them. You will use the latest code and you will develop your own. These are just samples, not the real numbers. Okay? They don't mean anything. Just telling you that one combination is for strength, we multiply the dead load by 40% increase. Many people question that. Why do we need to increase the dead load when we know the dead load cannot be changed? Once you make the slab, it's going to be there. Why do we have to change the dead load? So, dead load factor has been reducing gradually from 1.6 to 1.5 to 1.4, some cases 1.3. So gradually people are reducing the load factor or the safety margin for dead loads. Live load 1.6, sometimes 1.7, sometimes. So that is where the design codes will differ. They do not agree on what should be the load factors. And that is why a design, same building, same location, same loading, same material, same everything will come out to be different design by one code and different design by another code. And both of them claim to be right. By definition, two things cannot be right if they are different. One has to be wrong, one has to be right, or both of them have to be. So that is a challenge because the codes do not seem to agree yet on which way to go on the load factors. That is why the first lecture I told you, we don't believe the codes so much. We don't want to worry about the load factors. We want to remove all load factors completely and deal with real loading, real capacity, no load factors, so that there is no debate on these factors. And then you can see some are more, some are less. Sometimes we increase the loading, sometimes we reduce the loading. This especially 1.9D plus 1.6 wind, because of the upward effect of the wind. So we want to underestimate the dead load and overestimate the upward wind, like in steel structures. But on the other hand, these are serviceability checks. They are normally, the dead load is just 1 all the time, live load is often 1 or reduced, and so on. So these load combinations are the critical part of your design and must be listed in your design criteria document. At least the basic ones, right? And then that will become input to your program. Many engineers simply use the default load combination in the program, which may not match with what you are trying to do. So this should be listed and checked. These are some other load combinations which may be created by the program automatically, which may not match with what you want to do. You can see some factors match, some do not match. So you need to make sure that the load combinations that you specify are based on the code that you're using and are correctly incorporated into the program. Now comes the problem of the envelope pin. I think I showed this result last time, so you remember a little bit, that if there is load case number 1, load case 2, load case 3, there are m load cases, there are n load combinations of that, so there is a whole matrix, and out of that we could find the total by adding all of this load combination, multiplying this load case by the corresponding load factor, and then adding them together. So that horizontal equation becomes a column in this table. And from this one, then we can find the maximum P and minimum P, and that will become our envelope, right? But we already know that envelope is something that we cannot use. This slide we talked about last time. We need the action sets because of the interaction. So that is why we normally cannot use the enveloping. And we also talked about the design actions for static loads, combination, action set, combination, load cases, design actions obtained. So this is like a matrix, three-dimensional matrix from which we take out one block at a time to check for the design. Right? So 3 items together form a set. They cannot be separated. They must be taken as a set all the time. Axial load, moment X, moment Y, for the design of columns together, for the beam, bending moment, shear and torsion together, and for slab, MX and MY and MXY together, and so on. So all the time, every time we have normally 3 actions or 4 actions that must be designed together, not independently. So envelope cannot be used. Now this is what a typical combination will look like. That is only for static loads, loads that do not change with time. But when the dynamic loads come in and nonlinear loads come in, situation becomes far more complex, far more difficult to handle, because 2 things are happening. Imagine now start of an earthquake. Building is static. You have a certain column properties. Let's say the column is not cracked, so cross-section property is being used, and everything is fine. Now, after 0.01 second, the building moved a little bit in this direction. At that time, because of the inertia and everything, forces changed, and because of that change in force, now the cracking may have started, properties may have changed, so now it's a different model altogether. So the model must be updated to calculate the forces at this location, but the displacement has already happened. So we must start from there for the next time step. So we have to keep track of both time and displacement state, plus structures modification, nonlinearity at that time. So combination, now, so let's say the earthquake lasts 30 seconds, and normally we will analyze that in 3000 steps, right? About 100 steps per second or something like that, right? 3000 steps. For each step, we will check the nonlinearity at least 10 times in 10 small steps so that we don't miss any nonlinearity. So 3000 multiplied by 10. 30,000 times the structure must be analyzed to make sure that you will have the nonlinearity and dynamics included. That means for earthquake, there are going to be 30,000 load cases coming out. Then they must be combined with dead load and live load, and if there is any other combination of that. An earthquake, this direction, that direction, and others. So it obviously becomes a very large number of data that will go to the load combination table. Sometimes for the program, it takes longer just to combine the results than to do the analysis. In some building cases, it may take 1 or 2 days for a very fast computer just to get the combinations from all the load cases that it has analyzed. Okay. So it's a very, and obviously by hand it cannot be done. We have got to, and then there are options to cut it short. Response spectrum, for static load case, for each load case, one value goes to load combination. For response spectrum case, one positive, one negative value goes because the response spectrum has no sign. So whenever we get a value from response spectrum, we must use both positive and negative. So 2 values will go into the combination table. For time history load case, option is 1 for each time step, which is 3000, let's say, or 1 for envelope. If we don't care about what happened in between, we just take the maximum whenever it happened and add that to the combination. That is a shortcut. Not static nonlinear load case, 1 for each load step or 1 for envelope. Again, so we can decide whether we want the whole history or we only want the maximum value that occurred. The problem with the envelope is that the time of the, let's say later we are going to design a column for mx, my and peak. The maximum p, maximum mx and maximum my will not occur at the same time. So now you are trying to combine 3 numbers which actually never occurred together. So that makes it incorrect. Because maximum mx moment may have occurred after 10 seconds of earthquake, maximum my moment may have occurred after 20 seconds of earthquake, and maximum p may have occurred at 25 seconds of earthquake, right? So now you are trying to combine a condition which in fact never occurred together. So that's why combining the envelope results for time and nonlinear analysis is not really correct. But sometimes to save time, we can go ahead and do that. Alright? But all of these things you need to write down. How are you going to do that? Are you going to use envelope combination or are you going to use stepwise combination? So nobody can argue later. They already know what you plan to do. Response spectrum. Response spectrum, when we go to this one in detail, as I mentioned, we need positive and negative value. But the problem is that we have 3 sets, 3 actions to be done together, P, Mx and My. So which means positive negative combinations of all of them must be considered. So it will not be 2 load combinations, but 8 that needs to be added to that table. So for every response spectrum case, you will need to add 8 values into the combination table. So if you have 3 response spectrum and then earthquake, wherever earthquake comes, you need to do it 8 times. So the point I'm trying to convey to you is that combining the results is one of the most difficult thing to do for the analysis, to be able to combine the right results at the right time for the right properties. Because gravity load occurred for a structure which was undamaged. Earthquake load occurred when the structure is already damaged. So you're trying to combine 2 things which actually do not correspond to the same structure anymore. not at the same time anymore. So these complications make our analysis more and more difficult. The more we think about it, the more complicated it gets. If you don't think about it, it's very simple. Apply the load, add earthquake, we are done, right? But as we go into the details, you realize that most of those numbers actually do not make any sense, right? This is what is happening in a time domain. So with time, the response is changing. Bending moment is going up and down, negative, positive, changing all the time. So every time interval, the value is different. And this is the maximum, this is the minimum, this is the envelope value of the response. Right? So envelope value of response we can calculate, but we do not know which. This could be different, this would be different time step, not at the same time step, and different actions, different time step. Shear happening here and here, moment happening here and here, axial force happening here and here. So then you try to combine those which actually never happen together. So this, in reality, the structure never experienced that case that you're trying to create. When the moment was maximum, maybe the load was minimum. Maybe when the moment x was maximum, maybe the my was not there. So you're trying to create still a situation which never happened. But to simplify, we sometimes do that. Wind load case, as I mentioned, typically wind x, wind y, and wind diagonal should be considered as a minimum 3 cases. And of course, plus minus, so become 6 cases. Right? Could be negative, could be positive in each direction. So it will become 6 cases automatically. But in reality, when we do wind load testing and we apply it on real structures, we do at least 36 directions every 10 degrees. And then we put them there. Right? So you can see those load combinations. We will add both positive and negative, and 3 combinations. The total becomes 6 combinations for wind. And in the beginning, if you remember, 0.9 W, so that means when it becomes 0.9 W, it will become 6 times 0.9 W. When it is 1.4 W, it will become 6 times 1.4 W, because there are 6 cases for that particular case. So it just becomes a huge number of tables. Now, seismic load criteria goes much beyond, as I mentioned to you, than simply specifying the zone now. Previously, you just specify the zone is enough. Zone 1, zone 2, zone 3, zone 4, and your job is done. And you put that into the calculation and numbers come out. Now, our knowledge has increased, fortunately or unfortunately, and things have become complicated. And there's a famous saying, the more you know, the less you know. So it's exactly happening. The more we know about things, we realize that we don't know much. So we try to keep on adding always. Materials. Different parts of the structure will be using different materials. Again, simple building, you normally only specify one concrete will be enough. But not in the case of tall buildings. Tall buildings, slabs, columns, shear walls, foundations, all of them will be using concrete of different strength. And not only that, columns at lower level will use higher strength. As you go along, the column strength will decrease. So not only the concrete in every structure type is different, it also varies with height. So that means you cannot just specify a concrete strength of 21 or 33,000 and say, oh, I'm done. You will have to define maybe 20, 30 concrete material types, and then apply them to the right part of the structure where that particular material is used. 10 stories, different column, 5 stories, different column, this column, beams different, slabs different, foundation different, retaining walls different. So it creates the difficulty in terms of managing the data, because so many materials have to be created. So even if the column size is the same, material is different, you need to create a different column type in your model. So modeling becomes much more involved. Rebar, similarly, you need to specify different diameters, different bars may be used, right? So you need to specify. So all of these parameters are very important and they need to be discussed and specified because all of the analysis will depend on these numbers. Now we come to the hardest part of the process. So far, of course, loading is very hard, you already know that. And previously, there was no choice. A few years ago, this was not even a problem because there is only one method, hand calculation. Static, what you can do with your hand and what the handbook will show you and what the codes will tell you. So this question was not even a problem. Everybody had to do the same thing. But now, situation has changed so much that this becomes a major factor. What are you going to do for the analysis? Preliminary analysis and detailed analysis. What techniques you will use, what software you will use, what methods you will use, what options you will use, what parameters you will use. So much data, so much things that can differ between one engineer and the other because options are too many. So some people may select that, some people may select that, answer will not match. So now you can argue that how come same building, 15 engineers all coming up with a different design. So who's right and who's wrong? And it cannot be actually decided anymore because the parameters will govern your answer. So we need to agree on the parameters first. Calculate, review the preliminary response such as mode shapes, natural periods, base shears, story drift, lateral displacement, and determine size of primary structural components based on something. Okay. Rough estimation of what is going to be. Some of it can be done by hand, some of it needs to be done on a computer program. Quick initial model. After that, once you define everything, then we go to a detailed design, perform detailed analysis, design of all structural members, connection, stability, and each element, detailed drawings, and so on. So clearly, there are 2 steps to do. Now, procedures. We are going to do, first of all, the number one analysis that we are going to perform. Unlike other buildings, small buildings, you don't care about this one. Tall buildings, the first analysis you need to perform is the modal analysis. Not dead load analysis, which is okay, which is required, but modal analysis because tall buildings we define as a building which is governed by lateral loading. And lateral loading is related to modal analysis. Have you already heard about modal analysis? You know what it is, right? Fine. So modal analysis is the first one to be done to understand what's going on, which will then be used as a basis for all other work. And then we need to look at dead load and part of the live load to be included there. And then we look at sufficient modes to be included. How many modes are there in a tall building? 3 multiplied by number of floors is the number of modes that you will need to consider. But then after that, we can eliminate some that do not, are not related to us. But actually, at least 3 multiplied by number of floors is starting number. So it is, if it is, of course, by experience we can reduce that. But the actual number of modes which are important are that many. So 30-story buildings, about 90 modes should be looked at, or at least, of course, we may find finally that we only need 20 out of that, but we cannot know in advance how many we need. How we will know how many we need? Later. This is just a criteria, otherwise too many things to discuss. So we will decide, we will we will find a way to determine how many modes do we need, right? We cannot know in advance, but we need to do a lot to make sure that we get all. Linear static analysis then needs to be done. You know what is linear static analysis? Static loads, elastic materials. Response spectrum analysis needs to be done. We will talk about that quite a bit. Dr. Manning will talk about it quite a bit. All of these things will come up, but these are part of the rules that need to be specified. Then there are other analyses which are not mentioned here. Time history analysis, linear and nonlinear. Stage construction analysis, later to be considered. Okay. Temperature analysis, thermal analysis, later to be considered. Analysis for buckling, later to be considered. So there are going to be a lot more than this one that we just described, and I will go into them later. So there are at least 5-10 more types of analysis that we may need for a wall building, in addition to the very basic 3 that we have just talked about. Normally, what codes tell you, of course wrongly, is that you should use crack section for seismic analysis. You should use cross section for wind analysis. Now my question is, what happens? Today an earthquake came and tomorrow wind will come. The structure is already cracked after the earthquake and you are still basing your wind analysis on cross sections. What sense does it make, right? Also, earthquake will not crack everything, only few portions. And even wind may crack a few members. And gravity may also crack some and not some. But code will ask you to apply same uniform cracking factors to all columns and all beams. But in reality, columns in the lower floors may crack, uppers will not crack. Beams will, some corners here and there will crack, others will. So it's total chaos in terms of what the code is telling us to do in terms of using these factors. And why these are important? Because they completely change the results. For example, if it's a frame, right, it's an indeterminate structure, and I apply a load, and first, the moment of inertia of all members is equal, and I calculate the bending moment in column and beam. And then second time I multiply the moment of inertia of the column by 0.5 because I think it's cracked. What will happen to the bending moments? Moment will increase in the beams, right? True. Why? Because the moment will follow the stiffness, and if the stiffness of the beam is relatively higher than columns, more moment will shift there. And similarly, if I decrease the moment in the beams and not in the columns, the moment will flow to the columns and reduce the beam. Now, two situations will give me safe and unsafe results. If one situation will give me unsafe moments in the columns, another one will give me unsafe moments in the beams. So that means the real cracking and assumed cracking will give me very different results for the analysis, which may be safe or unsafe depending upon which cracking factor in the code happens to be correct, which is neither, right? So that means that this whole code approach to the crack properties is actually very incorrect, but unfortunately that's all we have for now. And for the tall buildings, we try not to use this approach and we go for nonlinear analysis, right? But we will talk about later. But of course, not many people are doing it. Very, very few, maybe less than 1% engineers are using that. So 99% engineers would not be using, and they will just use the code numbers, which will lead to, we don't know, safe or unsafe results. But this is something that you need to write in your design criteria. So another person who's maybe more knowledgeable or less knowledgeable than you should know that this is the assumption that you use. So normally we write down, I'm going to use cracking factor for column so much, beam so much, for wind so much, earthquake so much, right? The funny part is that we then try to combine the results of dead load and wind load and dead load and seismic load, which have been calculated on different structural properties at different times, and we assume that they are compatible, which they are not. Correct? So what should be the right way to do this one? What do you think, if you were the person writing the new design analysis procedure, what do you think is the very right procedure to go? What should be done ideally? What is happening in the real structure? What is happening in the real structure? Think about that. Why can't we just follow what is really happening? What is really happening is that the dead load and live load is being applied first, and then that loaded structure is being subjected to earthquake movement. Not independently calculate dead load, live load moments and add to independently calculated earthquake moments and combine them together. No. The dead load and live load come to the structure. Now the dead load and live load moving together during earthquake. So this effects must be calculated first without earthquake and without wind, locked in, and then subject this structure to earthquake loading with changing time and changing properties, and calculate which column is cracking when and modifying the properties at that time for that column and that beam. Anyone has any problem with that? Isn't that the right thing to do? Or you have any disagreement? Just follow what is happening. Try to mimic or try to analyze the structure the way it is actually behaving in reality, rather than trying to divide. For example, if the structure is being built up in floor by floor, your models should also be built by floor, not complete model at one time. So, really what should happen for a tall building analysis is this. The model should be built floor by floor, loaded by the dead load floor by floor, completed the entire building, apply the live load 25%, assuming that not everybody is there in the room, and then apply the earthquake at the ground the way it is shaking, not apply forces. Shake the ground, and then see how the structure is going to move. As it moves, modify the properties as they happen and where they happen, and continue until the earthquake finishes, and then see what happens. And go back and check every member, what happened to it during that whole history. Correct or not? Logically, that should be done. And that is exactly what we will try to do in this course for the tall buildings. Basically, we need to decide how we are going to model our things. Frame element means just a line, a thread. But column is not a thread, column is not a line. Column is this huge big thing in a tall building, 2 meter by 2 meter. Right? That big column, it's not just a small column. Shear wall is running from there to there, that thick, 1 meter thick wall we are talking about. How do you model them? How do you represent them in the model in a realistic manner? Then, insertion points and offsets, I will talk about that, what does it mean? And releases, we will talk about all of this, very modeling in the modeling chapter. Slabs, how we will model the slabs, shell elements, membrane elements, plate elements, rigid diaphragm assumptions shall not be applied, right? And this is something that people have been using all the time. So we say, no, diaphragm is not rigid, right? So if not rigid, then what is it? So how do we model that? And how does the diaphragm affect? So these are all going to be questions, but you need to clearly specify that I'm going to use this. And then stick with that. Shear walls, shell element, meshed wall elements, orientations, many questions. These are the questions that you need to answer at the time that you develop your criteria. So you understand what you're going to do, everybody else understand what you have done and they can check the results accordingly. Now, to be able to do all of that, obviously you will need to understand all the details behind each decision, because each decision will take you from this way to that way. It's so different. Rigid diaphragm, you go in a very simple way, your model becomes very simple, very much with less results. You choose not rigid diaphragm, you go another way. Much more complicated, but much more useful. Right? So every decision will give you more information, but will increase your work. Damping. How much damping to use? 5%, 2%, 1%, 10%. What is damping? Where did it come from? How can we increase it? How can we decrease it? How can we play around with damping to change our results? But you need to specify what damping I'm going to use and why. Right? Acceptance criteria. Finally, how are you going to say that my design is okay? What limits you will check? Right? You need to write down that my criteria is that if drift is less than this one, I'm going to accept it. If the deflection is less than this one, I'm going to accept it. Then you have to stand by it, defend it. Right? And sometimes we change these limits, and then you need to say, okay, I change it because this one. So that is just an overview of the entire process and the decision making that you need to do. The things that you need to know, the things that you need to decide, and the things that you need to follow up and complete them when the design is done.